A predictive AI project can look technically impressive and still be useless to the business. The model may train correctly, the accuracy score may look good, the charts may look convincing. But if the team predicted the wrong thing, used the wrong historical data, or measured the wrong outcome, none of that matters. Predictive AI does not start with an algorithm. It starts with a business decision that can be improved by a prediction. One of the easiest ways to waste time on predictive AI is to start with the technology. Someone says, we should build a machine learning model, or let's try XGBoost, or we should put this into Azure Machine Learning. Those may eventually become reasonable technical decisions, but none of them define the problem. A much better starting question sounds like this. Can we predict inventory shortages 14 days in advance accurately enough that purchasing can take action? That sentence gives us far more information. We know what we are predicting, we know the time horizon, we know who will act on the prediction, and we know why the prediction matters. Before choosing an algorithm, I want several things defined. First, the target. What exactly are we trying to predict? Units sold, machine failure, customer cancellation, late payment, project cost? Second, the prediction horizon. How far into the future does the business need to know? Tomorrow? 2 weeks? 3 months? The horizon can completely change the problem. Third, define the decision. If the prediction changes nothing, then the business value may be close to zero. Who receives the result? What can that person actually do? Fourth, define acceptable error. No predictive system is perfect. A forecast that is off by 5% may be excellent in one process and unacceptable in another. A false positive in a marketing campaign may cost a few dollars. A false negative in predictive maintenance could shut down a production line. The organization also needs to define the value of getting the prediction right. What does a stock out cost? What does excess inventory cost? What does unplanned downtime cost? What does customer churn cost? Without that business context, an accuracy score floats around without meaning. This is why the algorithm comes later. First define the target, the prediction horizon, the decision, the acceptable error, the business value. Then choose the technology that fits the problem. That sequence sounds less exciting than starting with AI, but it is much more likely to produce something worth putting into production. Once the business question is clear, the next job is turning historical business activity into something a model can learn from. That usually means identifying two broad things. What did we know at the time, and what eventually happened? Suppose we want to predict next month's sales. The outcome we eventually want the model to estimate is next month's sales. In machine learning terminology, that outcome is often called the label or target. Then we identify the information that may help explain that outcome. Previous sales, product, customer, region, price, promotion activity, season, holiday periods, weather, economic conditions. Those inputs are commonly called features. The concept is straightforward. We give the model historical examples containing inputs and outcomes. It looks for patterns that help estimate the outcome for new cases. But the quality of those inputs matters enormously. Imagine two models. The first sees only last month's sales. The second sees last month's sales, the same month last year, region, product class, promotions, pricing, holidays, and whether the customer recently changed contracts. The second model has more context. That does not guarantee it will perform better, but it has more information available to explain why sales may change. That leads to an important principle. Context improves the opportunity for prediction. More columns are not automatically better, however. Some fields may be noise, some may be redundant, some may not be available at the moment the prediction has to be made, and some fields may accidentally reveal the answer. For example, if we are trying to predict whether an invoice will be paid late, we cannot train the model using information that only becomes available after the invoice is already overdue. That creates leakage. The model appears brilliant because we accidentally gave it information from the future. This is where technical knowledge and business knowledge intersect. A data scientist may understand modeling. A database professional may understand the tables. A developer may understand how the application records events. A department expert may understand what those events actually mean. You usually need all of those perspectives. Historical data becomes valuable training data only when we understand the business process behind it. The objective is not simply to feed the model more data. It is to give the model the right information that would actually have been available when the decision was made. Forecasting problems are different from many other machine learning problems because time itself carries information. Tuesday may resemble other Tuesdays more than it resembles a random Saturday. December may resemble previous Decembers more than it resembles June. And this year's sales may depend heavily on what happened last week, last month, and last year. One common pattern is trend. Maybe demand has been increasing steadily for 3 years, or perhaps a product category is slowly declining. Another pattern is seasonality. Retail demand may rise during the holidays. Air conditioning service calls may increase during summer. Manufacturing volume may drop during scheduled shutdown periods. Then there are cycles. Some patterns repeat, but not necessarily at perfectly fixed intervals. Economic conditions, construction activity, commodity markets, and capital spending can move through broader cycles. Lag is another important concept. Yesterday's value may help predict today's value. Last week's workload may help estimate this week's workload. The previous 12 months may provide context for the next month. Moving averages are one simple way of smoothing short-term noise so the underlying direction becomes easier to see. And external variables may add additional context. Weather, fuel prices, interest rates, promotions, school calendars, supplier lead times, local events. A demand forecast may become much more useful when the system understands that a major promotion begins next week. Time series forecasting also creates an important validation problem. You cannot casually shuffle all of your historical observations and pretend time does not exist. If you train on information from December and then test whether the model can predict October, you may accidentally create an unrealistic evaluation. In production, the model only gets information that existed before the future event. Your testing process needs to respect that same boundary. The important idea is not that every business leader needs to understand advanced time series mathematics. The important idea is this: historical data has order. And when time influences the outcome, the model, the features, and the testing process all need to respect that order. That is what turns a generic prediction problem into a real forecasting problem. Forecasting is important, but many predictive AI problems are not really forecasting problems at all. They may use the same historical business data, but the output is different. Regression is commonly used when we want to estimate a numeric value. What will this project cost? How many hours will this service request require? What will this property sell for? What will the customer's lifetime value probably be? Binary classification is useful when the outcome has two primary states. Will the customer churn or not? Will the invoice be paid late or not? Will the machine fail within the next 30 days or not? Will the transaction be fraudulent or not? Multi-class classification extends that concept to multiple possible categories. A service ticket might be classified into several issue types. A quality problem might be assigned to one of several defect categories. Anomaly detection asks a different question. Instead of predicting a specific known outcome, we may be looking for behavior that is unusual compared with normal historical patterns. That can be useful in fraud detection, manufacturing quality, system monitoring, cybersecurity, financial transactions, or equipment telemetry. Then there is ranking or scoring. Sometimes the organization does not need a hard yes or no decision. It needs priorities. Which customers have the highest churn risk? Which machines deserve inspection first? Which invoices are most likely to become collection problems? Which sales opportunities deserve attention? A model can produce a score or probability that helps the organization rank cases. This distinction matters when designing the application around the model. A forecast might appear on a planning dashboard. A classification result might trigger a workflow. An anomaly might create an alert. A ranking model might produce a prioritized work queue. The output format should match the operational decision. That is another reason not to begin with the algorithm. Start with the question. Then determine whether the business needs a number, a category, a probability, an anomaly signal, or a ranked list. The prediction format should fit the decision the organization needs to make. That keeps the AI capability connected to the workflow instead of existing as an isolated model. Raw data does not automatically contain the business meaning a model needs. The database may contain dates, quantities, codes, prices, and identifiers. But the business understands something more. It understands context. Consider a manufacturer. The system may contain a production date, but an experienced operations manager knows whether that date falls during a planned shutdown week. The database may contain sales numbers, but the sales team knows a major promotion began that month. A customer record may show declining order volume, but the account manager knows the customer changed contracts. Those details may materially change the interpretation of the historical data. Feature engineering is the process of turning useful context into inputs the model can use. For example, instead of giving the model only a calendar date, we might derive day of week, month, quarter, holiday indicator, fiscal period, days until shutdown, promotion period, season. In inventory forecasting, we might create features for supplier lead time, recent stockouts, rolling sales averages, product category, or whether a replacement product recently launched. In project forecasting, we might include project type, customer class, team size, change request volume, previous schedule variance, and percentage complete. These are not just mathematical transformations. They represent business knowledge. This is one reason I am skeptical of approaches that treat enterprise AI as though you can simply dump a large data set into a model and let AI figure everything out. Sometimes the model will find patterns, but it does not automatically understand the organization's fiscal calendar. It does not inherently understand why one factory closes for maintenance every July. It does not know that a specific customer category operates under different contract terms. It does not know that an inventory shortage artificially suppressed historical sales. Without that context, the model may learn the wrong lesson. Subject matter experts often know these exceptions instinctively. Database professionals know where the data lives. Developers know when and how the applications create it. Analysts understand reporting definitions. Operations leaders know when the historical record reflects normal activity and when it reflects an exception. Strong predictive systems combine all of those perspectives. Data plus algorithms plus domain knowledge. That combination is usually much more valuable than simply choosing a more sophisticated model. One of the most dangerous sentences in predictive AI is, "It worked on the historical data." Of course it worked on historical data. The real question is whether it can perform reasonably well on data it did not already learn from. That is why predictive AI normally separates data for training and evaluation. The model learns from one portion, then we test it against observations that were not used to fit the model. This is the basic idea behind holdout data. For forecasting, we need to be even more careful because the order of time matters. Suppose we have 5 years of monthly sales. A realistic evaluation might train the model using the first 4 years and then test how well it predicts portions of the 5th year. That better reflects what production will actually look like. Use the past to predict the future. Backtesting extends that idea. Instead of evaluating one historical cutoff, we repeatedly move through history. Train through one point, predict the next period, measure the result, move forward, repeat. It tells us whether performance remains reasonably consistent across different periods. Leakage is another major risk. Leakage occurs when the training data contains information that would not actually have been available at prediction time. It can make a weak model look extremely accurate. Then production arrives, and the magic disappears. Overfitting creates a different problem. The model becomes extremely good at explaining the particular historical examples it has already seen, but poor at generalizing to new cases. A model that memorizes history is not necessarily useful for predicting the future. Then there is one of my favorite tests. Compare the model with the current baseline. If the business currently forecasts next month by using the average of the previous 3 months, compare against that. If planners use last year's value plus 5%, compare against that. If a simple statistical model already performs extremely well, compare against that. A sophisticated model should earn its complexity. If a simple method produces nearly the same business result, the simpler method may be easier to explain, deploy, maintain, monitor, and support. So a credible evaluation process asks, did we hold out realistic data? Did we preserve the time boundary? Did we avoid leakage? Did we check for overfitting? Did we backtest? And did we beat the existing baseline? A model is not useful because it fits history. It is useful because it demonstrates a reasonable ability to generalize beyond the history it learned from. Technical accuracy matters. But technical accuracy is not the final objective. A predictive system exists because the organization wants to improve some real-world outcome. Depending on the problem, technical teams may use metrics such as mean absolute error, root mean squared error, mean absolute percentage error, precision, recall, F1 score, or other measures. Those metrics help us understand model behavior. They are necessary. But executives usually care about a different set of questions. Did stockouts go down? Did excess inventory decline? Did overtime decrease? Did equipment downtime improve? Did collections increase? Did customer churn decrease? Did schedules become more accurate? Did margins improve? Those are business outcomes. Imagine 2 forecasting models. Model A has slightly better mathematical accuracy. Model B is easier for planners to understand, integrates cleanly with the existing purchasing system, produces results early enough to act, and reduces stockouts by 12%. Which one is better? From an operational perspective, Model B may easily be the better system. The business does not get paid for minimizing an abstract error metric. It gets paid for making better decisions. This is where AI projects can go wrong. The technical team optimizes the model. The project dashboard celebrates accuracy. Leadership sees a high percentage and assumes success. But nobody checks whether the process improved. That is not enough. A production predictive system should connect technical metrics to operational metrics. For example, forecast error may connect to inventory carrying cost. Churn prediction may connect to retained revenue. Failure prediction may connect to downtime. Payment risk prediction may connect to collections. Workload forecasting may connect to overtime and service levels. The strongest business case usually contains both. We need technical evidence that the model is behaving reasonably, and we need operational evidence that using the prediction actually changes the outcome. The distinction is simple. Model accuracy is an engineering metric. Business improvement is the objective. When those two remain connected, predictive AI becomes an operational capability instead of a modeling exercise. And that is the standard enterprise teams should use when deciding whether a predictive system deserves to move from prototype into production. Predictive AI works when the business question, historical data, model design, validation method, and operational metric all point toward the same outcome. The organizations that get this right will focus less on impressive algorithms and more on whether predictions actually improve decisions. You can explore more practical enterprise AI resources at ain.net.com. Thanks for watching.